Why is that the case? Because let's strictly thinking 1D first, and we are going to be generalizing that to multiple dimensions. So let's just think of an interval, right? Let's think of an interval where something, let's say certain molecules, can come in and come out of the interval. Okay, so so let's say the density of the molecules is described by a rho, and let's also imagine how fast the molecules are traveling is also dependent on rho. Okay, actually, let me give a more concrete example. Let's just think of these. I mean, a good example of a one-dimensional domain for conservation is a road. So let's say we have a road with a single lane, and all the cars have to travel just on the single lane. Nobody breaks the traffic law. And let's say rho, instead of being the density of molecules, being the density of cars. Okay, so rho is the density of the cars. And let's also imagine, which makes a lot of sense, that how fast the cars can travel is a function of how dense the cars are packed, right? If nobody else is driving, I can go up to the speed limit, but like if there are too many cars, I have to slow down. Okay, so basically, if my velocity is a function of rho, then what happens to the integral of rho between A and B? Of course, rho is a function of x and t, right? So how would the integral of the density, which means the total number of cars, right, in this interval, how would that change over time, right? Think about conservation of cars, right? We assume the cars doesn't appear or disappear out of nowhere. It either have to come from upstream or pass through our interval through downstream. Then what is this derivative? Yes? 0? Well, it depends on if I take the interval to be what. If my A and B actually goes with the flow, then actually I agree with you, the derivative is 0, because if I take A to be the location of one car and B to be the location of another car, right, then basically if no car is passing each other, then the total number of cars in between is fixed. But how about if I fix A and B as fixed locations in space? Like A is let's say a stop sign over a certain place, and B is another stop sign further down the road. Then the derivative is not 0, right? I mean, I can have a car that drives from upstream of B into my domain, and the cars is going to increase. And every time a car drives out of the domain, my car will decrease. So how can I mathematically represent this derivative using something? Using the principle of conservation.
Flux.
Yeah, flux, exactly. Right? How do I write it down?
I don't know how to do it with discrete cars.
Well, okay, so yeah, I don't know how to do with discrete cars either. But let's think about the cars being teeny tiny, and we have a huge amount of the cars, right? Think of continuous cars.
It's like rho v.
Exactly, right. So
hat.
yeah, so actually it's actually equal to the number of cars per unit time that passes A minus the number of cars that passes B in a unit of amount of time. And the number of cars that passes A in a unit amount of time is actually the density at a times the velocity at a, right? And then minus the outflux at point B. Agreed? So in general, such a function being a stricter function of rho, being the conserved variable, here is rho, is actually the flux. F is a function of rho. I mean, you can see like why I'm using F here, because F is actually the flux. Right? So this is just an example of saying that the time derivative of the total amount of conserved quantity within a certain space, a rho, is actually can be written as the difference in the flux between the ends of this interval. And now this is true not just for a single A and B. This is true for all possible A's and B's, right? And if rho is actually a differentiable quantity, if both F and rho are differentiable, then from the integral form to the differential equation, it's just taking B to be A plus epsilon. Okay, right? If you take B equal to A plus epsilon, then this is actually d dt of rho times a delta times epsilon, right? I mean, if B is equal to x plus epsilon, A is equal to x, right? Then this is basically the du dt times epsilon, and this is basically partial f of rho partial x times epsilon minus, right? Because I'm taking B B minus, oh yeah, so this is A minus B, not B minus A, sorry. So this is A minus B. So because I'm having left minus right, so there is a minus sign in the spatial derivative. And then if I move, if I get rid of the epsilon and move the spatial derivative to the left hand side, I get the differential form of the equation. So what I'm trying to tell you is that yes, I can only derive the integral form for equation that can be written in such a form, but all conservation laws can be written in such a form. Okay, that include all the gas dynamics equations we solve in computational fluid dynamics and a lot of other equations. All right. Any questions? Okay, so I think we are out of time, but like this is the basis for our finite volume discretization, which we are going to be talking about in the next lecture. So in finite volume discretization, we are not going to be solving for point values, but we are going to be solving for these kind of integrals or averages over small volumes, right? That's where the finite volume comes from. The volume from A to B, or the interval, is these kind of finite volumes. And instead of having the spacing of grids being small to approximate the derivative, we are going to be directly approximating this kind of conservation integral forms. All right, see you Wednesday.